I can't emphasize this enough. Whenever you approach a problem, you must use all the symmetries. You have to simplify it. Now, in the 19th century, they picked only the problems in which there was so much symmetry that, in the beginning of 20th century, there was so much symmetry that by the time you used all the symmetries, you just had to solve one-dimensional problems. So typically, you have something in 4 dimensions. You're solving general relativity in Minkowski space. But you say, let me look at the spherical solutions. So then I change my coordinates, and there's no information other than the surface of the hypersphere in the angular part. I only have to do the radial part, and what do you know? I'm in a prison camp, First World War. My name is Schwarzschild, and I write the solution. Now, this only happened in early 20th century. Late 20th century, we don't have this luxury anymore. We actually have to solve problems which are not translation invariant. So what happens is, if you look at a cloud, I move it a little bit, it's a different cloud. It's no sense translational invariant solution. I don't see that there is a translation in that solution. That's called broken symmetry, and people get Nobel Prizes. For example, Higgs boson and Phil Anderson in condensed matter, who did it first, realized that solutions of equations of motion don't have to have a symmetry. So, for example, you have a bunch of magnets, and equation has a property that if you flip north pole to south pole, the equation doesn't change. So, equation is symmetric. But when I look at my solution, they're all pointing up. Why is that? Because, that's one solution is they're all pointing up, they're all pointing down, in a phase where they're frozen and stuck. So the solutions typically don't have symmetries, but equations do. And this is the whole subtlety of how you use symmetries. Right now, and I'm telling you, if equation has a symmetry, in this case, simplest one, translation, where I put the origin of my coordinates, use it. And the way I use it is called Fourier analysis. It was invented for a totally different reason in 1840s or something. And so it gets to be subtle because, you have to use the symmetry of equations even you don't see them in solutions, and then it becomes a different course on group theory and how to use symmetries. But you should have the basic things that if you're given some solution which is asymmetric, Fourier modes could be stupid, could not be. Maybe they're not the best way to solve the problem. If you have symmetry, always use them.